Hi everybody. In this video we're going to talk about our third and final motion that we'll discuss that Earth has in this class. We have talked about Earth's rotation, its in the daily changes that causes, the diurnal changes. We've talked about Earth's revolution, its orbit around the sun, and the annual changes that causes, and the seasons. In this last one we're going to talk about the precession of Earth's rotation axis. So I know in the previous video with seasons, I had mentioned that the axial tilt, 23.5 degrees, always points towards Polaris. I apologize, that was a little bit of a lie. The direction that it points in, not how much it's tipped by, changes very, very slowly over time. And to help understand this, I want to go ahead and demonstrate what precession is, since that's what we're going to be talking about. I have a tool right here called a gyroscope. You can think about it as a very, very fancy top. So what I'm going to do is I'm going to get my gyroscope started. Let me go ahead and give it a nice. So now I have a spinning gyroscope, and I'm going to set it here on this. You'll notice that the top of the gyroscope is wobbling around and around. I mean, tops wobble, right? Let's see if I can get an overhead view. So you can see that wobbling around and around and around. What do we call this wobble? That wobble around and around and around is what we call precession. So now that we've seen that things that spin, just as a consequence of physics, spinning things experience perception or precession, let's actually go ahead and take a look at the precession of Earth. So Earth has its rotation axis. It rotates, got my handy globe right here. It rotates upon its rotation axis, which makes the Earth a giant top spinning in space. And any spinning object, its rotation axis will slowly change its orientation as it spins. That's what I was just showing with the gyroscope. That's what you can see in this video down here. The top part of this top wobbles around and around. So that wobbling of a top, that motion that of it's changing where it's pointed, where the rotation axis is pointed, that motion is called precession. And the Earth, being this giant top in outer space, will precess. It will experience precession. What does that mean? It means that where the North Pole of the Earth points to on our celestial sphere, what star it points to, slowly changes as the Earth makes one complete precessional wobble. So keeps 23.5 degrees, but where north is pointing is rotating around and around and around as the Earth precesses, as it wobbles. Why didn't I mention this before? It's because this is a very, 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 very long cycle. One wobble of Earth's axis takes 26,000 years. So one precessional cycle is 26,000 years. All right, so what is really changing as the Earth precesses? And there are two main things that we're going to talk about. It's going to change where the North Pole points to on the celestial sphere. So right now it points towards Polaris. It will point towards different stars in the future, and it's pointed to different stars in the past. And that cycle of it pointing, say, we'll start it at Polaris, for it to wobble around, point at different parts on the celestial sphere, and then come back to point at Polaris again, takes 26,000 years. So every 26,000 years, Polaris is the North Star. And there'll be a couple of other North Stars along the way. For the Egyptians, because of precession of Earth, the North Star was not Polaris, it was a star called Thuban. And it's right where the North Pole, the rotation axis of the Earth, pointed to on the celestial sphere. So it changes where the North Pole points to on the celestial sphere. It changes the location of the North Celestial Pole. And then also it'll change the orientation of Earth's axis with respect to its orbital plane. Remember when we talked about seasons, it was very important. If the North Pole was pointed directly towards you, and again, you on the screen will be the sun. Here, the North Pole is pointed, the tip is directly towards you. This would be summer solstice. But if the axial tilt is wobbling, if it's precessing, then that orientation is going to change. So over a quarter of a cycle, what was A solstice will now be an equinox. Halfway through the cycle, the solstices will have switched. Let's go ahead and take a closer look. So what I have right here is Earth. Here's the orbital plane, also called the mark where the ecliptic is on the celestial sphere. And here we have Earth's rotation axis, and it's currently pointed towards Polaris. So currently, Polaris is our North Star. So a star up in this direction would be Polaris. Then you can see that where north is going to point, I will represent by this circle on the sky. So where our north celestial pole will change as the Earth wobbles and points two different directions. So currently, in the year 2020, it is pointed towards Polaris. About 6,500 years in the future, it will be pointed over here in this direction. In the year about 1500, or about 13,000 years, half a precessional cycle, half of the wobble around, the star closest to due north will be Vega. So Vega will become close to our North Star. It's a little bit further away from where the North Celestial Pole will be, but it will be used in much the same way that Polaris currently is. And then another quarter of a turn, so 6,500 years later, the North Celestial Pole will be here on the celestial sphere. So we're a quarter or 3/4 of the way through the wobble, and then it'll be back to Polaris. So where the North Pole points on the celestial sphere is wobbling around and around and around. If we actually were to look out onto the celestial sphere, our fixed background of stars, we could draw the circle that the North Pole is pointing at as the Earth wobbles around and around and around. Where is it pointing? And we could draw that circle amongst the stars. And we would have our precessional circles. This is where the North Celestial Pole will be, which is going around in this circle every 26,000 years, every precessional cycle. We are right here with Polaris. You go to about 3000 BC, so 5,000 years ago, the North Star was Thuban. Then it slowly progressed and advanced until the North Pole of the Earth was pointed towards Polaris. It'll go through the constellation Cepheus, go past Deneb. So here about the year 15,000, it'll be closest to Vega. So where the North Pole of the Earth, where the North Celestial Pole is rotating around and around and around once every 26,000 years because of this precessional motion of the Earth, the fact that the Earth is a rotating top in space and spinning things precess. Which brings us to a discussion very similar to whenever I talked about the solar day and the sidereal day. Just like we could define two different days, now we can define two different years. Let's go with the easier of the two first, and the one that you probably think about every time you go 1 year. I mean, heck, nerdy people even will say, hey, happy birthday, you survived another trip around the sun. So we have our 360 degrees of revolution, one complete orbit around the sun. That marks one type of year, what we call the sidereal year. Again, this is as measured by the stars. So the same right ascensions will be up as they were exactly a year before. So our sidereal year is our one full 360 degrees of revolution, not rotation, revolution of the Earth around the sun. This takes 365.256 days. This is what most people think a year is. However, the year that we live by, our calendar year, so every time you look at a calendar and you look at the dates on a calendar, that is not measuring the sidereal year. That is going by the tropical year. The tropical year measures spring equinox to the next spring equinox. So it is going from spring equinox all the way around to the next spring equinox. But because of the precession of Earth's axial tilt, when that occurs, if we had the spring equinox here, but then we accounted for the precession, Earth would have precessed a little bit, it would have occurred a little bit before in its orbit around the sun. How much before the sidereal one complete orbit? Just a little bit, by about 20 minutes. So vernal equinox to vernal equinox is about 20 minutes shorter than one complete 360-degree orbit around the sun. Not very much, but over 26,000 years, that'll add up. So that makes our tropical year, our calendar year, measured from vernal equinox to vernal equinox, spring equinox to spring equinox, equivalently summer solstice to summer solstice. That's about 20 minutes shorter, which makes it 365.2422 days. Now you might be wondering about this. That's roughly 365.25-ish. You might be, that's kind of weird. Every 4 years, there's an extra day. And then you're like, oh, every 4 years, there's an extra day, a leap year. So that's why we have a leap year. And if you really look into all the rules of a leap year, you'll notice that it has extra rules for like every 100 years, every 400 years, things like that. That takes care of the fact that this is not exactly 0.25. Okay, so the tropical year is our calendar year. And why do we set that to be our calendar year? Because this is going to fix the seasons so they always occur at the same dates every year. That we always have summer in June. We always have our vernal equinox at about March 21st. Winter is always in December and January. It fixes the seasons to our calendar, because we're defining our calendar based on when the spring equinox occurs. That's great, because I would be really confused if we were talking about, say, what the Greeks were up to, and we were talking about the fact that summer now would have been like spring for them, and that just gets really, really confusing. But there is going to be a consequence. So what is the change? By fixing us to a tropical year instead of a sidereal year as our calendar year, well, the consequence is the time of year that a constellation is up at night is slowly changing. And I'll try to demonstrate this with Orion. So Orion is currently a winter constellation. It has a right ascension of 5 hours, which means that it's going to be at midnight crossing the meridian roughly around the December times. So a winter constellation. You can see it at night in the winter. So that's what I've drawn here. I've put the northern hemisphere in the winter. So notice that it's tipped away, the northern hemisphere is tipped away from the sun. So this would be northern winter. And here's the night side, and Orion would be over here. But if we account for the precession, that this will wobble around, keeping 23.5 degrees. If we wait 13,000 years from now, oh, sorry, that's supposed to be 15,000 CE, not 1500. I apologize for that. But we would, instead of being at the winter solstice, we would now be at the summer solstice for the same point in the orbit, because we've rotated from here 1/2 of a precessional cycle. So what was tipped away is now tipped towards the sun for the same place in the orbit. Because we've fixed all the seasons to our calendar, our seasons are still occurring at the same time of year. But in 13,000 years, this would still be June, but now it's the nighttime that we can actually see Orion. So Orion has become a summer constellation. If you think about this with the signs of the zodiac, then all of those signs are changing. 13,000 years from now, they'll be complete opposite. So if you're a summer sign of the zodiac, in 13,000 years, that'll be a winter sign of the zodiac, except they don't account for that. So really, everything's about a month off. So if you were born a Gemini, you're not really a Gemini, you're a Taurus. Sorry about that. All right, so I said I also want to show you this just quickly using Stellarium. So I'm going to go ahead and stop sharing here and bring up Stellarium for you to take a look at. So what would this actually look like from the ground? And I'm going to make this full screen for me. So I just have this turned on to, looks like it's right about now. Let's pause time. And for this, I don't want to worry about daytime or nighttime. So I'm going to turn off the atmosphere. I'm going to turn off the ground, still looking towards the north, right above it, Polaris. And what I'm going to do is I'm going to turn on that circle, that precessional circle, onto the sky. So right here, you can see the date is marked right here, 2000. So in the 2020, Polaris is still sitting right here at about due north. Polaris is our North Star. The year 7000, the North Pole will be, the North Celestial Pole will be this part of the circle. And we can see that. You're not really going to see it that much, so I'm just going to start advancing the year. Also notice 1, 2, 3, 4, well, 1, 2, 3, 4, 1, 2, 3, 4. We're seeing the extra quarter of a day, the leap year. Go ahead and hold this down, and you probably can't really see. Oh, I know what I need to do. I apologize for that. Pop up the equatorial grid. There's our North Celestial Pole. Hasn't really changed because I've only gone about 50 years in the future. Wait until this becomes a couple of centuries. And you can probably start to see just a little bit that the North Celestial Pole, where all those lines converge, is moving slowly away from Polaris. And now let's cheat a little bit. Let's go to the year 3000. 3002. Notice it sits right here at 3000. Now we're pretty far away from Polaris. Let's go to the year 8000. At this point, we don't really have a North Star. We might start calling something like this our North Star. Polaris is way over here, not at the North Celestial Pole at all. Let's go to the year 15,000. I feel like a Time Lord right now. So here we are at the year 15,000. Vega is close to the North Celestial Pole, so we might use that to set north by. It'll be a little bit off. So you can see where our North Celestial Pole points changes over very, very, very long time scales. Let's go to the year 28,000. Oh, almost a full precessional cycle. And look, Polaris is coming back to be the North Star. It's not exactly 26,000 years. It's a little bit longer. But you can see Polaris is coming back to being our North Star. So that would have been a full precessional cycle. Notice that, yes, this is simulating the sky for the year 28,000, which you can do with Stellarium. It is a very powerful program. Thank you for going ahead and tuning in to this video. Hopefully you understand that we have 3 motions of the Earth that we have to talk about in astronomy. There are a couple of more, but those are the big ones. We have the Earth's rotation. We have the Earth's revolution, its orbit around the sun, and we have the fact that the axial tilt, the 23.5 degree axial tilt, wobbles like a top, so it rotates around and around. It precesses. So the precession of Earth's rotation axis. All right, thanks for tuning in, and I will see you in next week's videos.